Osborne's dissertation defense. This is going to follow the regular protocol. Joe will talk for about 45 minutes or so. There'll be a short period of time after that for public questions. Then we'll ask everyone in the room to leave except Joe, and then there will be an hour or so of committee questioning. And then we ask Joe to leave the room, and the committee confers generally for about 20 to 30 minutes or so, and then we bring Joe back in to deliver the verdict. So with that, please welcome Joe.
All right, I can't resist a kind of fun title. So I'm presenting my dissertation defense, Operationalizing Operational Logics. I've been here a little while, and I would really like to express my sincere gratitude to all of you in the lab, to my committee, and also to my family, without whom I definitely would not have gotten this far. So thanks to all of you. Any kind of project in AI around games has to start by answering this question, but this is kind of an ill-formed question. I think it's maybe more useful to ask, what are the components of games? What are games made out of? What are the pieces? A common answer for this is the game mechanic. Game mechanics, they show up a lot in the literature around game design, in the craft practice of games. Robin Hunnicutt calls them, defines them as the actions, behaviors, and mechanisms afforded to the player supporting overall gameplay dynamics. So maybe a game is just a big set of game mechanics. Actually, this is also not a super useful way to conceptualize games. Here's two mechanics: lose 10 health when you touch a wall, pick up a power-up by touching it. There's some issues with these, right? Like they're not just made out of, they're not atomic. They involve a lot of different little pieces. So they also have some kind of shared structure. They're both, when you touch something, stuff happens. And the stuff that happens is also kind of similar across the two. Maybe some health resource changes. There are some differences as well, right? Like maybe the characters, like state changes. Maybe they get invincible for a while or something sometimes. So it's kind of non-regular, these mechanics. Another important thing is that if the player isn't aware that the mechanic is happening, it's very difficult for them to recognize that a rule exists. So stuff like feedback, like playing some kind of sound effect or changing the visual appearance of the character, is actually an integral part of the game system. But most discussions of mechanics they sort of bracket off feedback and communication to the player. So games aren't just the mechanics they're made out of. They're also definitely not just like the pictures and sounds you see on the screen. For a theoretical foundation for my game AI work, I needed a way to simultaneously address how games worked and how they looked, or how they communicated their inner workings to players. Noah and later Michael, Noah and later Noah and Michael developed this theory of operational logics. And that's what I've been basing my work on for the last couple of years. Here's a kind of roadmap for the rest of this talk. We begin with about half the dissertation, which is theory around operational logics, refinements and extensions to that theory. And the second half is case studies, places where I've used operational logics-based knowledge representations for AI projects in games. What's an operational logic? An operational logic fulfills a communicative role by implementing an abstract process tied to a game state presentation strategy. So an example of a communicative role is for collision logics, things happen when objects touch. Things might happen when objects touch. The abstract process there is check whether two rectangles overlap, or check whether two bodies overlap. And the state presentation strategy has to be that the position and size of objects on the screen corresponds to their position and size in simulated space. You get a projection onto a 2D plane or something like that. The communicative role of the logic describes how the logic needs to be used from an authorial standpoint. So how a designer has to deploy this logic in order to successfully communicate its operations to players, in order for players to recognize that the logic is present. For a collision logic, this is things happen when objects touch. For a camera logic, it's the world is big and we can only see a little bit of it at a time. And this also shows up in non-game applications with like scrolling text fields or websites or whatever. And for the entity state or character state logic, a character might have different behaviors or abilities at different times, depending on other stuff that happens in the game. The abstract process of a logic is a kind of specification for how it needs to work in order to function to fulfill that communicative role. For collision, it's about detecting overlaps between spaces. For cameras, it's about mapping a region of the world onto a viewport. For character state logic, it's sort of triggering the operations of a finite state machine and gating character actions based on those states. The game state presentation strategy, the final piece of an operational logic, explains how it is that players perceive the behavior of this operational logic in the context of a game. With collision, it's the projection on 2D space. For a camera, it's the smoothly scrolling view of the world where characters can move in and out of frame and they're clipped by the edges of the frame. And for character state logics, it's different animation cycles, perhaps, when you're in a different state, or a sort of and some indicator over the character's head to tell you what state they're in, for example. A really common type of game that we see a lot in the study of operational logic so far is the graphical logic game. You might also say like the action game, or games that are basically about continuous space and time, some kind of physical movement, and some resource transactions that happen. Also characters with fairly complex kind of state machine-based behaviors. This term graphical logics is used widely, and one move that we've made recently is to break it apart a little bit and say, while traditionally this is used to describe arcade games, action games, it's maybe useful to say it's a particular composition of collision physics, character state, and resource logics, which are generally communicated through graphical strategies. You can also imagine textual communication strategies or others. But it's sort of making this decomposition forces us to ask, how many operational logics are there? Is it only like those 4? And if not, like how do we count them? It's actually a particularly hairy question, because even if you're just looking at physics logic, the communicative role of which is that objects can move or change according to physical laws. In other words, it captures differential equations as an authorial affordance. That can mean a lot of different things. It has to, I think, at least capture smooth movement in space. But some physics logics will address momentum. Some physics logics will address wind shear. Some physics logics will address thermodynamics. So I think it's useful to say that physics logics, for example, are a family of logics. We can treat them as a family which communicate physical behavior. The goal of some work I did a couple of years ago was to catalog and identify these different families broad families of operational logics to try to keep the total number relatively small, which is important for problems in knowledge representation, because you want to have a kind of fixed finite set of possible things you have to care about. So I did a lot of work thinking about like which games to include in this like corpus of games to look at and consider what kinds of logics are present in these games. I played through and thought about these games, trying to explain stuff which was happening, the movement of things on the screen, the display of user interface elements, and so on, in terms of either existing operational logics or hypothesized new ones, based on a procedure that we followed in 2015 for a different paper about game interpretation from an OL standpoint. The key trick here was making sure to avoid explanations which were like super awkward or that only reflected an abstract process or only reflected aspects of the presentation. So I'm going to talk a little bit more about what a good explanation is for a game phenomenon. Let's say you're in a game with extra lives. You have 99 lives. You cannot get any more lives. You walk on the 1-up thing and you don't pick it up, or you pick it up and it doesn't increase your number of lives. So it has a pretty natural interpretation as a resource, like a resource pool with a maximum capacity. If you were playing devil's advocate, you could probably make an argument that it represents a physical space which gets filled up, that there's the little extra life icon you pick up is getting moved somewhere, and after a certain amount of time, no more of them can go in because they're blocked. They can't get in. But this is not a great explanation because it doesn't really have much to do with the player's sort of lived experience or perception of what's happening in the game. And if there's a phenomenon or some process or both which are not well explained by the logics that you've identified in a game so far, that may be an argument that you have a new logic that you didn't know was present, or maybe a new type of logic that didn't exist. One type of operational logic that I think had been hypothesized in some of the earlier work around 2009 was the idea of like a growth logic, metaphorical growth. Like you have a character that gets stronger over time. It's like growing up, it's getting bigger. And that's certainly something you do in a role-playing game, right? Your strength statistic goes up, your intelligence goes up, you're fulfilling the like Bildungsroman of the role-playing game. But you can also do growth with a collision logic, right? There's a pretty natural way to indicate growth with collision, which is that your collision volume gets bigger. So I don't think a growth logic is a kind of meaningful family, because there's no, what it means for a collision object to grow and what it means for a character to grow is not reconcilable, or at least they're not the same thing. So I don't think that there's a place for something like a growth logic. We're also interested in avoiding logics which are redundant. So that's the kind of opposite tension. A logic's redundant if its communicative role can be expressed through other logics' communicative roles, not necessarily through their processes. This isn't about the overlap of, say, well, like physics and continuous resources are kind of the same thing, but their communicative roles are wildly different. Vision in games is another case kind of like growth, where there's a lot of different things that you might call vision. There's the sliding camera that shows you a different part of the room at different times. There's this kind of light cone that's projected in front of the character, and ambient light when you light up a torch. That's a very different kind of vision than this kind. And there's also this idea that when you walk in front of an enemy, the enemy sees you and starts moving towards you. Like the enemies have vision as well. But these types of vision are actually like incredibly distinct. They're really different things. And they communicate very different things. The idea that you can see part of a larger environment is due to camera logics. The idea that agents may or may not see other agents sometimes, that's kind of more connected to the state machines of those agents and collision logics. So there's no need for any kind of agent vision. But we do need a camera logic because there's no way to interpret, for example, in Doom, when the character is moving around and the stage, their first-person perspective of the stage is changing, it doesn't make any sense to say that the level is sliding around underneath you and you have a fixed viewpoint. That's like a nonsense interpretation, even though it's actually what happens in the code in many ways. So these are all of the operational logics families, asterisk, at least the ones that have been identified so far. It seems like a suitable set. We haven't really modified it substantially since 2016, I guess. So now we can return to the mechanics. Mechanics are made out of pieces provided by operational logics. All this stuff about if you're touching something, then some stuff happens, and you need to communicate that the collision happened, that's collision logics. Those are operations from collision logics, operations and game state presentation strategies. Character state logics take account of the change in the character's state machine. And resource operations govern the increases and decreases in health. It's not shown here, but probably there would also be some code to update GUI elements reflecting, the amount of health the player has, like a bar or something like that. Now, okay, here's new stuff that wasn't in previous publications as much. Operational logics compose together. What we saw on the previous slide was one way, called an operational integration. Operators of logics do something when you collide or increase a resource by an amount, has some kind of holes in it that need to be filled in, either by constants or by terms from potentially other logics. So looking back at lose 10 health when you touch a wall, we have an operational integration between collision and resource logics. The second kind of composition is structural synthesis. This is the glue that gives you connections between the different ontologies of these different logics. So if you're thinking about a video game where there are characters that move around, and the characters also everybody has a health resource or something. It's a structural aspect of that game that anything which moves around also has a health resource pool, and that these are connected with kind of the same name. At the same time, this one entity has also a collision volume and also physics behaviors and also character states. That kind of bundle of all those things together is a structural synthesis. Another example of structural syntheses is in crafting systems in games. So in Diablo, for example, where you have an inventory where objects are laid out kind of spatially on a 2D grid, but the crafting system is just interested in how many of which objects you have. So being able to project from one representation to another representation is a structural synthesis. These are often game or genre specific. Finally, we have communication channel sharing. So any logic may define certain communication channels. So you might have, for example, with a collision logic or physics logic, the idea that you can communicate information in the spot on the projected 2D plane where the character is. So you might pop up a number over their head or make them play an animation or something like that. In resource logics too, you have this idea of maybe a dedicated part of the screen where you show readouts for how many of different resources you have, and you can multiplex other information onto those same channels. So entity state logics, another word for character state logics, they are changing the sprite or appearance of an entity. Resource logics are showing maybe empty or full bars or floating numbers above physical entities. Or if you have a game mode logic at work where you have sometimes menus, sometimes the main screen, sometimes game over screen, that also affords particular communication channels that other logics can communicate through. Okay, we did it. Reading games with OLs. How do we interpret games through an operational logics lens? So this is a game called Street Fighter 2. It's about fighting, street fighting. And the way that we know that is by playing it. Well, certainly by the name of the game. But also we sort of observe that there are characters and that when we move our joystick, the one that we're controlling moves. There's this timer that's counting down. When you push buttons, stuff happens on the screen. So we see that there are certain logics at work. There are control logics, game mode logics, collision logics, character state logics, because the things that you can do at different times depend on the buttons that you've pressed recently. There's also resource logics. When certain collisions happen, this bar at the top goes from yellow to red for the person who was struck. So there's a lot of different phenomena happening in this game. And by sort of paying attention and doing a close reading, you can aggregate out the operational logics which are present. There's also a game mode logic. Sometimes the game ends and you get this kind of interstitial title card thing. So fighting is going on. If I'm looking at it from the perspective of a player, thinking what's going on in this game, there's fighters, they're moving around, they're using their bodies to do different attacks. There's some kind of physics modeling for whether attacks are successful, there's characters can block attacks or they need to strike to work. Fighters have some kind of reaction when they're struck. And then the matches are structured through some sort of state machine. So the question of whether there's fighting in a game, for example, is maybe better phrased as what kinds of properties of the experience of playing the game have to be present or justified in order to argue that combat is happening, that fighting is happening. This was work that we presented at FDG in 2015 that brought in proceduralist readings from my trainer and others into this operational logics grounding. So proceduralist readings are a way of mechanically, formally arguing that a game represents a concept or that a game communicates an idea. The key notions here are that there's stuff happening in the system which is invisible. There's stuff happening on the screen which the player can see. And there's outside cultural knowledge that the player can bring in to frame their interpretation of their observations of the game's processes, and thereby construct meaning. So when you want to claim that Street Fighter is about fighting, you used as evidence like the pictures and sounds, like sounds of fists hitting people and pictures of burly guys and girls. And you combine those observations with your understanding of processes at work in the game, which model aspects of that concept. So the idea of like a formalized match, where there's like a time limit and multiple matches are sequenced in a set. The idea that the health bar is sort of like a fighter's stamina or their like will to keep fighting, and when that's depleted, they it's like a knockout in boxing or something like that. And you connect this to stuff that you know about the world, movies that you've seen that feature this kind of fighting, or your awareness of boxing as a sport. The best arguments for such a claim exclude the least evidence of stuff which is happening in the game, and include the fewest external conjectures or interpretative leaps, as Mike Trainer calls them. A reading in a proceduralist reading is a goal of interpretation. It's like what you're building towards in your interpretation. And one project that I pursued in the dissertation is to reformulate them in operational logics terms, to show that this sort of new theory we've built up is applicable in another context. So I argue that operational logics give sort of axioms or atoms of interpretation which are consistent or inconsistent with particular readings. They give, in other words, the arrows in one of these derivation trees. So if we want to make a claim that A is destroying B, or A is killing B or something, we can build that if we understand that when A collides with B, B disappears, and A looks like something that can hurt B. If it's the head of a person and a hamburger, we would not say that the person is killing the hamburger, we would say the person's eating the hamburger. So it's important that it be more like, I don't know, like a person and a bomb or something. So the role of operational logics here is to help transition from stuff that's happening in the code to stuff that's happening in the player's mind. So the understanding of what is going on here. Operational logics also help you combine these lower level interpretations with information that comes from outside, from your cultural frame. Now, some of those arrows are not accounted for by operational logics, and that remains important future work. Playable models are another important way of reading games, which I've been reframing in an operational logics context. Playable models have only really been expressed, as far as I know, in some presentations that Michael has made to different audiences at different times. And it comes from his earlier work on agency and the poetics of simulations and authorial affordances. So what's a playable model? Playable models support interactive and gradual exploration of a simulation model so that an interactor can develop a mental model that provides them with effective agency in the system. So already we're talking about a couple different kinds of model. There's the thing that's happening inside the system, which could just as well be in a spreadsheet or in like a batch processed weather simulation or something. And a mental model, which is only in the interactor's head. So two different senses of the word model here. What's key about playable models is that they involve the interactor in the process of unifying the simulation model and the mental model through experimentation, through gradual interactive exploration. And the key to this process, or the sort of end result of this process, is the interactor gaining the ability to make plans and execute those plans inside of the system. And this development of agency, this process of learning how to play, learning how to sort of see through the black box or summarize the system in a useful way, is key to playable models. So like proceduralist readings, playable models discuss how games communicate ideas, and they're phrased in terms of how players interpret what's going on inside of the game. Some key differences, though, are that playable models are about internalizing a model. And although it's not explicit on the previous slide, playable models require some kind of transfer. So if you already know something about urban planning, you should be better at playing SimCity than someone who doesn't. And also, after playing SimCity, you should be better at urban planning, or at least according to some theory, than somebody who had not played it before, and also had a similar background to you beforehand. So to summarize playable model theory, a game's a black box where the player can apply their outside knowledge and experimentation within the system to reverse engineer the model or summarize it in some kind of way, which creates new knowledge inside the player's head. And maybe it's knowledge that the game designer doesn't even know. Operational logics are at work in two places in playable models. First, they provide the machinery for the underlying simulation. Anything that happens in a game, you can say operational logics are at work, almost. We'll talk about that maybe later. And the communication channels and the syntheses of these logics in this game give the player ways to climb that ladder of understanding, or rather they make some kind of the membrane between the player's model and the system model more permeable. It's important to note that models are different from logics. Playable models are not the same as operational logics, because you can realize a particular playable model in a bunch of different ways. So you can have a model of space, maybe with a collision logic and a physics logic. That gives you a kind of continuous space. But you can also model space with linking logics, where you have a graph of connected points. Text adventure games, for example, or even the kind of space like higher order space in something like The Legend of Zelda, where you have different rooms, although within the room you have a small continuous space. But there are other combinations that can give you space as well. The game Midas, which is in PuzzleScript, encodes a model of physics, gravity in particular, but it has no physics logic. It's only about spatial pattern matching. So there are some, even though there are models of physics and there are physics logics, these are not the same thing. Models can also compose together in kind of a different way from operational logics, whereas operational logics compose according to a few sort of flat mechanisms. Playable models build up in more of a graph, or they build up taller. You can have more complex models from simpler models, which individually are combining outside cultural knowledge with operators and feedback from these operational logics. That was how we can read and interpret games using operational logics. But we can also specify complete game designs using operational logics. And this is also new material. So we can say that a game is made out of certain operational logics, which are composed in a particular structural synthesis, communicating across shared channels, and with this game's specific rules defined through a set of operational integrations. And there are also the kind of graphics and sound effects and level designs and monster behaviors and whatever that are in this game, which are all given in the ontology, which is implied by those earlier four things. So thinking about Super Mario Bros. 3, for example, where you have maybe like a title screen and that kind of like map mode, and then inside the game you're playing. In a sense, these are like three different games. But the logics at work here are some kind of persistence logic, because you keep your number of lives and stuff across different stages. There's a game mode logic governing when you make transitions between different modes and what you can do in each mode. So on the menu screen, it's only control and selection logics. Selection logics are picking one thing out of a bunch of things. Here it's just one player or two player. In the map, you have a linking logic which connects the different locations in the game world, and a variety of others which help persist state across different games, or get you into different stages. And within a stage, selection logics aren't really present, but you have some other new ones like collision and physics, which were not in the other mode. If we break down a game into logics like this, we can also get a procedural interpretation or procedural semantics for operational logics by picking an order of evaluation to say, First, we check if the game mode should change. Then we see what the sort of joystick or gamepad is doing, and we decide what the high-level control actions are. Then we see if the camera needs to scroll. We update character state machines. We update the physics simulation. We update the collision to sort of stop objects from bumping into each other. If you go down a pipe, then we take you to the place that the pipe goes to. And then maybe if you hit coins or something, like you get more coins, you get an extra life or something. So, and then loop around back to the beginning. This is something you can implement in code. So sort of march through each logic, update each logic individually. In the craft practice of game development, sometimes these things are called systems. You might have a collision system or a physics system or a resource system or whatever. And you end up with something like this. You have programmed a game. Individual logics would be implemented, perhaps, just as the implementation of their abstract process, maybe with some like effect system or something to communicate outputs along some parallel thing. It's totally like arbitrary code, but I think that there is a mechanical translation from an operational logic specification of a game to a programmed implementation. But we can also come up with a logical formulation. So the Gemini project is a project in game generation from our group, which I joined on fairly late with. But it's really interesting because it combines game generation and a formalized mechanized version of proceduralist readings, which we looked at earlier, in a logical framework called answer set programming that allows for crosstalk between these two. The idea in Gemini is to generate new games by constraining which interpretations players should be likely to make. So an example of a game intent file, as it's called in Gemini, the input to Gemini is to say, the game has to have hand-eye coordination. It needs something that the player does that has a risk-reward trade-off. There must be a resource, maybe the first one, which is good. And the goal of the game should be to maintain a high level of this resource, and you should be able to lose the game. But there shouldn't be any other changes like a winning or whatever. Also, the computer should control an entity in the game. And this is all encoded as facts and constraints in a logical framework. Now, Gemini commits to particular structural syntheses, the graphical logics that we discussed earlier, where you have game entities that have collision bodies, that have physics behaviors, that have resource pools like health. It also has a notion of like painting the floor with different colors or clearing the paint that's on the floor. But this is a specific structural synthesis that Gemini is kind of hardwired to do. It also is committed to particular ways of sharing communication channels and a constrained set of possible operational integrations that might be generated by Gemini. So there's a tight relationship, therefore, in Gemini between the kinds of readings that you can express, readings like the goal of the game is to do X or A hurts B, and the space of generable gains because of that logical crosstalk from earlier. It's troubling because readings have to be made by hand, whereas the thing which is using the readings is like a comprehensive, complete search. So there's kind of an imbalance of affordances there. Although I know Adam Somerville has been working to resolve the kind of made by hand issue. But also the ontology itself is somewhat non-orthogonal. So if we want to say A eats B or A consumes B, we have to have different readings for each case, whether A and B are both entities or like B, the thing being consumed is the health of an entity or the thing being consumed is a resource. Whereas we would rather write this as sort of A consumes B if A causes B to go down somehow or decrease somehow. And it's inconvenient to have to write it in a bunch of different ways to express essentially the same thing. So I had a project Constellation, which tried to reframe Gemini as an instantiation of this theory from the first part of the talk. Each operational logic was axiomatized as a logical theory with some query operators and some action operators and some ontology, which could be mapped in a structural synthesis to the ontologies of other operational logics. So Gemini star, Gemini in Constellation, again, fixes particular structural syntheses to say for every entity, there's a collider, a physics body, a resource pool, state machine. And it gives some mechanics which are common across Gemini games. And it also generates arbitrary combinations of the query and action operators as Gemini rules. Now, this project sort of stalled out because the Gemini readings had to be rewritten under constellations terms, and that was just a big knowledge engineering task I didn't have the time for in the end. But what's exciting to me about Constellation is that you can imagine lots of other game generators, and it would be ideal if you could share those readings, those proceduralist interpretations, across the generators. It's also possible to imagine other axiomatizations of logics. So right now we use one that's kind of timeless or time-free, and our physics, for example, is a qualitative model, but you could have a quantitative model of physics. You could have something that addresses time. And these axiomatizations, these logical theories are modular and they're also compositional. So the final part of my talk is going to walk through a few projects that I did with operational logics as the kind of theoretical foundation and how productive these have been for me. The key step here was recognizing that there's a correspondence between each operational logic, each of those families identified before, and formal logics or mathematical objects that have both similar abstract processes or sort of similar domains of discourse and connected authorial affordances. And this ends up being a really good foundation for knowledge representation. Plus, if we can make the bridge to like first order logic, then we can also integrate these corresponding formal mathematical logics in the same way that we integrate operational logics together. Here's a big list, you don't have to read it. We're gonna look at a couple specific combinations of these. So I did a project which looked only at recombinatory logics called reductionist. And this is based on James Ryan's expressionist language for text generation with some authorial control. That's written as a kind of context-free grammar, but it turns out that this grammar maps very well onto a logical concept called the symbolic visibly pushed down automaton. The details aren't super important for this talk, except that we can do things with this logical representation that you cannot do with search or with sort of treating the thing as itself. Like going to the logic is really helpful. For example, we can count how many possible pieces of dialogue could be generated by this system. The answer is 10 to the 64 for this particular grammar. And there's no way that you can, this is a histogram also of like how long each individual utterance might, how many utterances of each length there are. This is something that you just cannot do by enumeration because 10 to the 64 is a stupidly large number. Also, if you want to search this haystack and find a particular needle, like is there a way for me to introduce myself and say my name twice in the introduction or something, that's very difficult to do with search. And James came up with a lot of good tricks. And in this paper, we found that through this logical formulation, we could beat many of those tricks in many ways, although some of his special cases we weren't quite there yet. But the key here is that we saw this connection between recombinatory logics like dialogue generation and production systems or automata theory. Here's another project that we did at the PCG workshop called Mappy. And Mappy is a little AI system that runs through video games and builds maps. But what's interesting about its maps are that it distinguishes between smoothly scrolling continuous areas and like portals or links that take you to a different room that's sort of self-contained. So in Mega Man, it's like this. In Super Mario, it's like this. And the key tricks we used here were to recognize that the parts of the games that we were looking at were camera logics, linking logics, and control logics. We use control logics to know whether you're doing some kind of animation that's taking you between the rooms. On the NES, at least, this is a common convention that you lose control while you're moving from, for example, this room down this like pipe into this room. And Mappy is capable of constructing quite complex maps. Another project that we did in a kind of similar vein was to try to recognize or summarize game character behaviors as a kind of automaton, a kind of state machine called a hybrid automaton, which you can think of as a state machine that also is associated with some physics rules. What we wanted to do was to learn why a character changed from, say, like running to jumping. Maybe they pressed a button, maybe they hit something on the ground that caused them to jump. And we wanted to have movement equations in each state, so running, jumping, falling, whatever. But we didn't want to know in advance what the states were. So we started from zero information about that. It turns out that state machines are used very widely in game design as well. When Steve Swink, for example, talks about Mario as a concurrent hierarchical state machine, although he uses a different notation, the idea that a game character is specified by a state machine is not a new idea. So just as action game characters combine character state, collision control, and physics logics, hybrid automata combine networks of like fighting state machines, some kind of action logic to determine when to make a transition, switch systems of differential equations to give the different physical behaviors in each state, and some kind of Boolean algebra for deciding when to make the transition. It happened that because we were able to draw these connections between operational logics and formal logics, the particular formal object that results from composing these four things corresponds quite nicely to the game design object that you get when you combine these four things. So we did some work looking at pixel positions over time, collisions, and button presses, applied some statistical machine learning magic that Adam knows about, and came up with distinct physical modes. The green one and the blue one are different models, but the ones are the same. And then this like big dark line is ground truth. And turned that into a state machine by identifying which of those modes on that kind of hairy graph were the same, and aggregating those into groups and then looking for transitions between those groups. This was really successful work. It was a big improvement, I think, in hybrid system identification. At least the IDPI reviewers thought so, which is pretty cool. And I think that this has applications outside of games, or as I should say, applications in things like general game playing, where it might be helpful to come up with a summary of a game character's behavior so that you can do like hypothetical planning or something like that. Or you can pull out a game character from one game by observation and then plant it into a different game. This stuff isn't only useful for like machine learning and recognition, it's also useful for modeling. So this is another way to write that Super Mario from before with like running and jumping and moving left and moving right. And I think it's interesting to ask, like, can we actually use this as a kind of game making tool? So I did. This is a system called HypeHead. I'd been working on it for a little while, and then I had a bunch of undergraduate researchers come through on it. And with one of them, I ended up doing a paper on planning, like motion planning. So these are a couple of scenarios. Here's like a little character that can move left or right. This platform is also moving left or right at a fixed rate. And this one begins moving left or right at a fixed rate once you step on it. So even though it seems quite simple, it's actually a quite challenging planning problem, because if you just try to move right as fast as you can, these won't be in sync. So you won't actually be able to make it to the other side. So any kind of greedy search or even heuristic search is going to do very poorly for a very long time. Likewise here, heuristic search is going to try to jump straight up towards the goal, up and left, because the goal's to the left. Whereas the right behavior is to go away from the goal and then come towards the goal. I think that there's a lot you can do with this. So we did stuff with incremental search and rapidly exploring random trees, and it won best student paper at AID. But I think it's interesting to also think, like, what can we do with the logical representation, the sort of declarative representation, instead of only relying on the simulation. So it's easy to know that if you start here, you can get anywhere in here, and that if you start in here, you can get anywhere in here. You can just look at the state machine and understand that's an invariant. It's harder to know that if you can step onto here, you can ride this platform to get anywhere in here. Likewise, it's harder to know that you can do the same thing on this platform. But what I think is super interesting is, as a person, we formulate some kind of plan that's like, I'm going to get to this one at the right time so that I can get to this one so that I can get to here. Those little jumps are really challenging, and I'm excited about the idea of tackling problems like that. So open questions. That was our run through of some different systems. This work needs desperately a more robust account of cultural knowledge. It's mostly bracketed off, but it is actually super important for stuff like playable models, stuff like proceduralist readings, and even for operational logics themselves. We also need to address a little more strongly, I also need to address, how it is that entities behave the way they do. So Pac-Man's ghosts, for example, have different behaviors, but from an operational logic standpoint, they're all kind of the same. They have collision, they move around. Right, so far, I've been leaving that to non-determinism, that the AI agent can pick what it wants to do from capabilities which are given by the operational logics. But I think it's probably important for the player. I think that the player knows something about how AI agents make decisions, how they do pathfinding, how they prioritize different actions. And I think that that has to live in operational logic somewhere, but I don't know exactly where yet. What I want to avoid is having like a new operational logic family for every different AI algorithm that might control game character behavior, because I think that's clearly the wrong way to go. I'm also very interested in pursuing this constellation work sometime and thinking about game generator generators. So if Gemini Star, for example, is defined in terms of constellation, but it would be easy to come up, let some of those parameters vary and come up with a different game generator, which then generates other game generators, and then other games. And also, especially for the logical frameworks like Constellation, so far game dynamics, like what's happening, like how players make decisions between different options or how players formulate sort of higher order behaviors of game characters, this is mostly unexplored in the work so far. I had an undergraduate working on some interesting stuff in compositional game analysis. So in something like The Legend of Zelda, you have different rooms in a dungeon, and it's interesting to ask whether you can solve the individual rooms independently and then combine those smaller solutions for a larger solution. And this has connections to like assumed guarantee reasoning in software verification. So I really would like to explore that more deeply. And I also think that, as I mentioned about camera logics earlier, they don't only show up in games. Operational logics show up in all kinds of interactive software. But maybe not all the same operational logics. Maybe there are some different ones that show up in like music players or cell phone apps and in video games. And it's also likely that the verification problems that people making websites or apps have are different from the verification problems that game makers have. So I'm interested to know how these kinds of techniques can support their work. So to sum up, just a few minutes over, operational logics, they're useful. They're helpful for human critics and helpful for game designers. They're super helpful for automated analysis. They're really good for computers. And they're productive as a knowledge representation. So in the year when I was doing work with like MAPI and HiPAD and stuff, that was a year when I had like 13 publications. And some of that was delayed from previous years, but a lot of it was just because we had happened upon a really useful and usable representation. And I think that other people can turn the crank on this and come up with other systems that use operational logics in a deep way. And I'd be happy to discuss that with anybody. So now I'm happy to take questions about the presentation. Thanks very much.
We have time for a few minutes of time for questions from the audience, I guess including the YouTube audience, if you see any from that channel.
They're still catching up to us.
Okay.
I'll start. I really like a lot of your work. This is a really good talk.
Thank you.
It's always been really, really sort of interesting to me and fascinating. I want to kind of like, so you talked sort of at the end here, and I want to like kind of follow up a little bit about sort of other sorts of automatic, generation systems, perhaps cache and operational logics for other domains that aren't games.
Mm-hmm.
What do you sort of see that being? Do you have like a good idea on what that might be, or is it still like really kind of up in the air because you're mostly interested in games?
Well, I think about, so I know there's been some work in text editors, for example, with like operational semantics for text editing, like the idea that there's selection and insertion and deletion and copy and paste and moving the cursor and whatever. And I think that it's clear that in the programming languages community where that kind of work comes from, there is an interest in modeling interactive applications, modeling interactivity. I think that this kind of operational logics work could be a nice starting point for that, because I think if you're only in like a text editor frame of mind, you're going to come up with a very text editor centric ontology that's not going to translate well to other systems. But I think that if you're looking at operational logics, you know that there are certain ways that selection gets communicated and what selection means, and there's certain ways to think about like scrolling and the viewport and stuff. I think that there are going to need to be other logics. I think that especially around like a lot of applications have kind of special purpose weird stuff, like video editors or something. Like it's not really clear. But I think the way forward for that would be to do the same kind of work that I did for the Operational Logics catalog, only instead of starting from a bunch of games and seeing how it is that I understand what's going on in that game, to instead start from a bunch of applications. Take a bunch of interactive programs and websites from different periods of time and say, what's happening on the screen and how do I form causal relationships between those things. I think the command line is a very interesting environment for that. I'm actually a colleague at Pomona is interested in doing command line verification of command line scripts and stuff like that. And I think that's probably the next step. Yes.
Do you know how a cluster make use of operational logics in a sub-symbolic setting? The context being there's all this exciting stuff happening with deep reinforcement learning, and sometimes if somebody could tell you, oh, you're playing a game that uses linking objects, you're playing a game that uses that, like, how do I exploit that knowledge inside of the neural network?
It's a good question. So for the work on hybrid automaton learning, we had that bias going in, and we picked a model that was consistent with that. So we picked segmented regression, which is like kind of a textbook machine learning thing. It's like it almost doesn't qualify as machine learning. But I feel like knowledge about what models are present, what logics are present, helps you in the model selection stage.
Not in the live learning stage. Like it helps the human who sets up the experiment, but not.
I haven't thought as much about the other scenario. I think that you could probably do something with like competing models. If you think about like the game could be made of this or it could be made of this, and over time you might determine through experimentation that it's made of one thing or the other, and then like prioritize the conclusions of that other model. I know that Tom Murphy had, I actually didn't mention it in the talk, but a lot of the work on learning from play was based on Tom Murphy's work on like automatic 3D-ification of NES games and using the game program itself as the source of truth about the game program. So he would had a little system that would do experimentation. Like if I put the character up here, will they fall down? And if they fall down, then maybe this game has gravity. Or if I try to walk the character into something that looks like that, will it stop the character's movement? And if so, that thing is probably colliding. And I think that those kinds of techniques, I mean, again, it relies on some knowledge engineering up front. But yeah, I just haven't put as much thought into the sub-symbolic setting because I'm a Chenkian like Yale School classical AI loser. Thanks. Yes?
Will the slides be made available?
Yeah, the whole presentation is recorded on YouTube, but I could also send you the slides if you like. It's a couple hundred megabytes, but I can send you a link if you want, or hit me up on Mastodon or something.
Great. Well, I think with that, let's thank Joe again.